to the second session of Contain the Code, which is containers from scratch. So in the last session, so this session again will be taken by me, Aditya, and Shantanu. Yeah. So in the last session, we covered what virtualization is and different ways you can virtualize. One was by using virtual machines, and then the other was containers. We also explored Docker, which is one you could say implementation of containers. It's a package which allows you to manage everything related to containers. You can create containers using that, package images, and yeah, pretty much do everything. And we learned how to create Docker images and create containers with Docker. So yeah, that was the first session. Today's session, we'll deep dive into what containers actually are, how they are internally represented, they work internally. So basically, pretty much everything which Docker does behind the scenes without letting you know. Yeah, we'll be learning about that. And again, tomorrow's session is going to be about container orchestration, which is basically automating your container management, the creation of new containers and managing them. Yeah, so that will be more, that will, in that session, we'll look more into Kubernetes, if you've heard of it before. Yeah, if you have not an issue, we'll be introducing in tomorrow's session. So yeah, moving on. Yeah, before we start, just you can always feel free to ask questions anytime. You can stop us in the middle, unmute yourself, or you can put the question in the chat. And still, if you are to, I don't know, if you don't want to just share it here with everyone, you can go visit this link. Shantanu has put it up on the chat also, and you can put a question there, and you can put it anonymously also. Yeah, and we'll answer it. But it'll be really good to see questions here, because this is like something a bit more, in detail session. So I'm quite sure there'll be a lot of questions, and if no one is asking it, it'll just mean that you guys, we are not delivering it well. So I hope we do deliver it well, and you guys have some good questions. Yeah. So moving on. Yeah. So containers are a feature of Linux. Yeah. So this is one thing that you need to note, that when we say containers, usually it means that it actually means that it's made for Linux. Okay. Linux is the operating system which provides features for you to create containers. You might think that you can run Docker in Windows also, but that's actually not an inbuilt feature of Windows. It's actually you would notice that you have to install WSL, which is Windows Subsystem for Linux, and then the containers run on that. So basically, it's still using Linux, right? So yeah, this is one important thing that you need to note down. Yeah, next slide. Shant. Yeah. So what exactly are containers, right? So in the last session, we saw that containers are basically, isolated instances which, virtualize some resources of the operating system, right? So when you create a container, you have a separate file system, you have separate processes. The processes that you run in the container are isolated from the ones running in other containers and the operating system. And yeah, pretty much even the network, like if you attended yesterday's session, that we saw that the ports of the containers are different from the ports of the host, right? The network ports. So they have their own networking. Somehow the networking resources are virtualized, and yeah. So that is what how we define containers yesterday. Right? But let's deep dive into what resources are actually virtualized, and what exactly does a container stand for, from the point of view of the operating system, which is Linux. How does Linux actually see a container, right? So when you are if you see from the point of view of Linux, a container is just a group of processes, all right? it's normal processes. It's a set of processes with some special resources, different some special, I don't know what you call it, resources allocated to it, right? But it's still in the end it's just a normal process. And that's why if you remember from yesterday when Shantanu had started inside a container when he started command sleep 30, and then if he did ps then when he did ps from the host operating from the host terminal, you could see the process actually listed in ps when you did ps ops, right? And that's because, again, as we said, containers are a container is just a group of processes. But there are certain things that are different. Okay, so for those processes, for those group of processes, some of the resources of the operating system are isolated, and those resources are users, networks, the file system, the process id, and they also have some kind of memory and cpu limits applied to those. So that given a container, you can specify that this container should not take more than say out of say more than 1 GB of RAM, or this shouldn't consume more than this much percentage of my CPU, right? So these are some of the things that are applied to those groups of processes which form the container. And how is that possible? So Linux comes with certain features which allows us to do this, and those are first namespaces. Then we have C groups. Don't worry about these terminologies, right? Don't just get intimidated by these. We'll explain what these are. Then there is capabilities, and there is seccomp bpf, which even I'm not sure about, and we can just skip it for this session, right? By the way, before we continue, this diagram that you see here, this was actually created by Julia Evans. She is a programmer and highly active on Twitter, and she creates these comics kind of things called zines, which explain which explain certain various topics in a very easy way. So this is from one of her zine about containers. She has various other zines on networking and others. Do check them out. So most of we have taken a lot of diagrams from our zines. So continuing. Yeah, and so I mentioned namespaces, and then so now before we can continue to what namespaces, C groups, and capabilities are, I think Shantanu can show a small demo of how we can first start from a basics, like what a process is and how can we start giving the process a special a separate file system, separate map of process IDs and all those things, and in the end basically isolate the process from another set of processes, eventually creating a container.
Yeah, hi. So I hope I'm audible to everyone. Yeah, I'm audible, right?
You are to me. Can someone else also confirm once? Okay.
Yeah. So I think someone mentioned, the slides link may be inactive to some people. It might show that it's closed. So I'll just try fixing that once. It shouldn't have said that. Okay, it does show it's closed. So I'll just try to fix that once, and then.
I've created
okay,
one. Actually, wait, just close that. I've created one. I'll share that link. You can close this and present again. You'll get the new link.
Okay, fine.
Yeah.
So if I go for the Q&A,
continue
recent, right?
Yeah.
Okay, cool. So this link is shared, right, with on the chat.
Yeah.
Okay, cool. Okay, so I hope this link sort of works. Okay, yeah, this link works. Yeah, so okay. So let me just zoom into my terminal a bit. So I hope this is visible to everyone, right? So let me know if it's not visible, because I'll be using my terminal a lot and it should be really bad if it's not, if the font is not visible. Okay, so yesterday's
Yeah.
session,
Can
if
you
you
zoom in a bit
remember,
more? Can you zoom in a bit more? Someone just said, Kapil says zoom a bit more. Yeah. Yeah.
now,
Is it fine now, Kapil? A little more.
okay.
Yeah, fine.
I think it should be okay now, right?
Yeah.
Okay, fine. Yeah. So yesterday we ran a command. For example, in Docker, run --rm -it ubuntu bin bash. So what this command does is it starts an container based on the Ubuntu image, and we saw what this flags do. --rm just closes the container after the bash quits, and -it is just to make it interactive so that the bash session works out properly. So when I click enter, so we notice a couple of things that happens after this. So we get into a terminal, and if I do ls, I see certain number of files here, and these files are different from the files I see on my host, right? So if I do the same on my host, I see a different set of files. So what I'll try to do now is I'll try to sort of achieve this. So I'll try to sort of create a process. So basically what's happening here? So what's happening here is the process that's running in this container, its view of the file system is different from any process other process that's running. So any other process that's running outside the container, its view of the file system is is the one that you normally see. But the one inside the container has a different file system, and I can make changes in this file system not affecting the host at all in any way. So I can create a directory, maybe call it container, and that won't affect my root folder, correct? So I don't see that file here. So we'll sort of try to achieve that. So I'll exit out of this container. We don't need the bottom terminal. So yeah, so I sort of already have a root folder of kinds. So there is an Ubuntu FS file. So that contains some sort of files that you have in your normal Ubuntu root folder. So what I want to achieve is I want to start a process whose view of the root folder will be this Ubuntu FS folder, and I don't want it to see any other files and folders in my host. So the way to do that is, so there is a command called chroot. So chroot is, I believe, short for change root, and so the meaning is, so what it is sort of obvious from the word itself, change root. So we sort of change the root to my given folder. So I can do chroot ubuntu fs, and if I click enter, okay, so I need sudo access. If I click enter, I get some warning. We can ignore that, doesn't really matter. But what we see is now I'm a root user in some folder. So if I do ls, so the contents of these contents are exactly same as these contents, right? And if I try to go backwards, I can't. So basically what happened is I was able to change the root folder of a process to Ubuntu FS. And now this process cannot see any other files in the system, any other files outside Ubuntu FS. So what we have done is we have sort of achieved, part of what a container is. So if you remember, when I ran docker run -it -rm, that long command, I went into a file system that's different from the host. So what Docker is doing there is it's also doing something similar to this. It is it has its own sort of copy of Ubuntu FS. Let's say this Ubuntu FS is I would say obtained from the Ubuntu image, somehow present there. It would have a copy of this folder somewhere, and then it would chroot into it, right? And when that happens, what would happen is its view of the file system would be different from that of the host. So I hope that aspect is clear.
Yeah, in case you're wondering what process was started when you did chroot Ubuntu FS, by default chroot, if you don't, the syntax is chroot, the destination folder to which you want to change the root to, and the process name that you want to start. So you could, after Ubuntu FS, you could put ls or something. But if you don't give that, by default, it tries to run the default shell of the user, the $shell variable which is set in your shell. So by default, it started /bin/bash. But if you give ls, it would just run this process. So yeah. Also, I think Shantanu, you can, if you you can. So just to show you that this thing is also true for Docker containers. If there is, Docker creates a certain, a similar folder when you created this Ubuntu. Yeah, when you create this container, right? Docker also creates this kind of folder under /var, under this under one of these uh, folder somewhere in /var, and there also you can find this setup. So it'll be under the containers folder and then the hash of the container somewhere there, right? But you can find it. Yeah, I think, I don't exactly remember, but it'll be somewhere in /var directory. Okay.
So the PWD of directory I'm in is var lib docker. So we should be able to find the folder it's currently in somewhere around here.
Yeah, you can go to temp or image, one of those, and you'll find it somewhere there. I'm not sure. But yeah, you can do it as a homework, like where you can find the folder, but it does unpack all this, and then the file system is present there. Okay.
Yeah. So okay. So I guess the chroot idea is at least understood for now. And chroot is not just used in Docker. I believe it's also used for other applications. For example, if you want to install packages, at least on Arch, if you want to install packages from somewhere, one of the advantages of chroot is, so if you have a process starting with its own root directory, all the dependencies. So what you can do is, so the root folder in the in the host can have some dependencies, and you can have some other file like Ubuntu FS, like I have, and there are some different dependencies altogether in this. So what you can do is you can sort of create an environment with different set of dependencies, and then you can sort of build packages. So you can have, so what you can do is you can have one program with different version in your Ubuntu FS file folder, and then you can hence build your project or something like that. I mean, of course, you'd use something like this even with Docker, but you can sort of achieve that just with chroot, given you have a root file system folder with the correct dependencies, right?
So, also, if you have, if you are someone who just likes to play with Linux and have tried installing Linux manually, or like Arch, there is no, there's no GUI installer for Arch, or automatic installer. You have to do everything manually. You would know that, even when you're installing from the ISO into your hard disk, you actually need to chroot before into the device of into your hard disk before you can start your installation. So that is also one place where chroot is used. Even when you use a GUI installer like Ubuntu, if you just notice those logs which it shows while installing, you'll somewhere see that it's chrooting into the root partition that you have mentioned while partitioning. Yeah. So.
Yeah. So I guess we can continue to namespaces now.
Before we continue, any doubts regarding this? Okay. I guess no doubts then. Just feel free to stop us at any time if you have any doubts. Yeah. Okay. Moving on. So now, what exactly are namespaces? So namespaces are, it's just a fancy name given to a kind of, a method to, somehow give different. So we have an operating system, which is Linux in our case, in case of containers here, and this operating system manages certain global resources of the system, right? So some of the common resources that you can think of right now is, the memory, the CPU, then the file system itself, and then you have your processes, then you have the network. So all these resources are being managed by the operating system, and these are certain global resources, right? They are global to all processes, to the and to the entire system. So these namespaces, what they do is they provide different views of the same global process. Okay, so what you can think of it is as, say you have a cylinder, right? And if you view it from one side, it might look like a rectangle, and from another side, it'll look like a circle. So though it's the same global resource, there are two different views of it, and that is what namespaces do. They give you, different views of the same resource. Now there are, multiple namespaces within Linux. Uh, yeah, if you want to find out how exactly they work internally, you will have to, dig through the Linux code and certain LWR articles and all those, and find out what exactly data structures and all I use and how it's achieved. But just letting you know that this feature exists in Linux. Yeah. So what namespaces exist? Yeah, we can move on to the next slide. Yeah. So one is the mount namespace. This was the first namespace that was created in Linux. Yeah. So what this does is, so you have, when in your system you have certain mounts, right? So you mount your hard disk, and there's different partitions. If you run the mount command, it list all the current, mounts that you have made in your system. So this mount namespace provides you a way to, isolate the different mounts in your system. So a namespace could only show you certain set of mounts out of the actual total number of mounts. Okay, so say you have 5 mounts. Then I create a mount namespace which only show you the first 2-3 mounts or something like that. Yeah. So yeah, that is the mount namespace. Then you have the UTS main namespace, which is, I think, Unix time sharing namespace. Yeah, Shantanu. Uh,
Yeah.
yeah. So yeah, it's the UTS namespace. It sounds fancy. It's nothing much, but it's basically at least in the current, today, it's just to provide a different host name for the system. So the name Unix time sharing, timeshare comes from in the code there is a certain struct. It's C code, so there's a struct which is named, which has the same name, and the namespace has something to do with that, because that struct contains the host name and, the name of the host, and that the identity, right? So this namespace can be used to change the, to give a different host name to a process. So suppose you start a new namespace and you have processes running with that namespace. The processes will get a different view of the host name of the system. So by default, if you would have noticed that when you start a container, the host name changes to some random hash, and that hash is the ID of the container, right? So that is achieved using UTS namespace. Yeah. Then there is the IPC namespace. IPC here is inter-process communication. This basically gives you, you would have learned about, if you had your OS course, you would have learned about the various ways of IPC, right? There is the most common is the pipes, right? So this namespace is used to, isolate those pipes to certain groups of processes. Yeah. Yeah, then here is the a very interesting namespace PID, which is something that you notice firsthand when you start a container. So as we notice, when we start a container and spin up a process, that process has some PID, say 8 or 9. That PID won't be the same, and if you try to view that process from your host, the PID will be different, right? And if you start another process, and if you start another container, you won't be able to see that process in this container, right? So PID namespace allows you to have same process IDs for processes, even in different namespaces. So what this means is, so normally if you had no namespaces and just one common resource, the PID resource, you would need unique PIDs, right? This is well known that the process IDs in a system are unique, and usually they are just, when you create a new process, it's basically the previous PID plus one, right? It's just incremented. Usually, it's not always the case, but yeah, that's how usually it's done. But with namespaces, what you can do is you can have two different processes with the same PID, provided they are in two different process PID namespaces. Okay. Yeah. And one interesting thing about PID namespaces is that they form a hierarchy. Okay. So you have the root namespace. It forms kind of like a tree. Okay. You have one namespace at the root, which is the default namespace, right, of the host. So when you create new processes in your host, without forget about containers or anything, that is the namespace which is used. Now, when a container creates a new namespace, for PIDs, this namespace becomes the child of the original root namespace. Okay, and what happens here is, and one common rule of PID namespaces is that the a process in a namespace can see all the processes running in its in its children namespaces. Okay, also all the namespaces that are below it, this process at the top can see all the processes in that, and that's why the host can see the processes running in all the containers, because the PID namespace created for those containers is actually a descendant of the root namespace, root PID namespace. Okay, so I know this was a bit confusing. So do you guys have any doubts about it? Let me know. I'll just pause for like 10 seconds or something. I think a diagram here would have been better, but like, yeah. So network namespace. Again, this is network namespace is used to provide different views of the networking resources, which is your the your networking sockets. I mean, what do you call that? Then your ports and even your IP addresses. All those things can be different using the network namespaces. Right. Next, user namespace. So this is another interesting namespace that you'll notice firsthand in containers. With user namespace, you can have uh, a separate. You have root with UID 0 on your host, right? Right. But in a container, when you open root, you can actually have that root as a separate UID. So what this means is that inside that container, this user with a non-zero UID will actually look like root, so that it becomes a zero UID. But to the host, it's actually a non-privileged user with non-zero UID. So it basically maps a certain set of UIDs and GIDs to another set of UIDs and GIDs. So yeah, this is the user namespace, and yeah, so you can learn. So this was just a brief summary of all these namespaces. You can learn more about these on the LWN article. This goes in depth on how these namespaces, what namespaces are, what each of these namespaces deals with, and also how you can create what system calls are provided by the Linux kernel to create these namespaces, and create a process with these which uses these namespaces. And yeah, uh, huh. So yeah, that's it about namespace. So any doubts?
Yeah, so I'll sort of show a demo of this. So the ideas, you can see them more in a concrete way, so that when you saw, like, theoretically it might be a little confusing, but yeah, I think, yeah, demo will help. So basically what I'll be showing is, so there is an awesome YouTube video wherein they try to code up a container from scratch by writing a couple of lines of code. So I'll sort of try to replicate that in this session, so you'll get a feel of what is going on behind the scenes. So we'll
Uh,
sort of try to, yeah.
we just have one doubt before that.
Okay.
Yeah, can you just present that? Do containers have any users except root? Yeah, so containers can have other users too. By default, there is only root, but you can, go into the container and create user using user add. If you don't want to do that, when you are executing the shell or starting the container or executing any command, in Docker itself, you can specify some username and some user ID, and it'll just log in with that. But you can definitely have multiple users inside the container.
Yeah. So okay. So yeah. So there are no more. Yeah, there are no more doubts. So I'll continue. Uh, yeah. So what I'll sort of try to show you is, I'll try to build a container from scratch, I would say, and it would sort of replicate what Docker does, but in a very minimal way, with only having very few features. But that'll sort of give you a very good idea of, pretty good idea of what's happening behind the scenes. And yeah, so maybe I can just go into the editor. Uh, yeah, I might have to zoom in. So is this visible, or will I have to zoom in more? I think this should be okay, right?
Yeah, if we Bhaskar, you were saying something?
Yeah, this looks okay. Like,
Yeah.
Okay,
Just
cool.
let us
thanks.
just put a message on the chat if you need us to zoom in. Yeah. We can continue.
Yeah, so yeah, I'll be using Go right now, but it's not necessary that you guys should know the Go language. So I'll sort of convey the meaning behind the syntax, and also the syntax. The syntax is not so different from other languages. So if you're familiar with some language, you'll follow along quite well. So yeah, so there is some code to write. Yeah. So so what we'll try to replicate is, so in the Docker command we ran was something like this, right? It was Docker run. There was an image. There was a command, and that command had some parameters, right? So for example, one of the commands was Docker run Ubuntu, and I could run a command like sleep 100, right? So the sleep would be the command here, and params would be 100. So that's like sort of an example. So what we'll do is, we'll try to sort of replicate that. So go run .go. So So this part is just getting the Go program. So this file is called main.go. So this line just sort of runs the program, and I would like to pass some command line arguments to this. So let's say the first argument is run, and we'll see later on why we need that argument, and then we'll pass the command we want to run, right? So if I sort of something like this. We will not pass an image to the command. It'll be apparent why we are not doing that, but so that's sort of what we want to achieve. So we want to pass a command with some parameters, and we want to run it inside a containerized application. So when this program is running, we want to run it inside one sort of a containerized way. Okay, so I'll just quickly write up some code to get that done. So we want to see if the first parameter, if the first argument is run, we'll call a function called run, and if by default we'll just panic and say bad parameter. Okay, probably this is the right syntax. Okay, so function. So we'll define the function run. So right now, just to see how it will all work out, I'll just print the output, printf, and I'll say running %v, I think, and os.args to run slice. Okay. So we'll run this program, and we'll just see what happens now. So we run the program as go run main.go run, and I'll say echo hello world. So right now the program is not doing anything really. So sorry. So as you can see, I'm just printing that this command has to be run. So that's also not happening. So firstly, we'll just try to achieve that. We'll try to run a command, and then we'll try to containerize it. So in Go, you can use a package called exec to do this. So we'll do that exec command, and the first one will be the command itself, which is in the second parameter, and the second parameter would be this, and then we'll run the command. And yeah, and if you just do this, it will probably not work because it'll run the command, but you won't be able to see the output. So if you want to interact with the process, sort of, you need to do some stuff. So this is not really important. It's sort of so that you can interact with the process properly and all that. So we'll just copy. So we have to do it even for std out, and we have to do it for std error. Right. So let's see if a code compiles now. Okay. So now you can see that I passed echo hello world, and it logged that command, and it also ran that command. So it echoed hello world. So right now we have just achieved running any basic command. It doesn't really do anything more than that. So let's start with the UTS namespace. So what I'll try to do is I'll try to now run my command inside a namespace. And since, as Aditya already mentioned, the UTS namespace, you can have different host names. What we'll do is we'll try to assign a host name to the container that's different from that of the host. Okay. So firstly, I'll just go inside a. Okay. So host name is when I write host name, this is outside the container in the host. I get sri9. So host name is in your command prompts right after the user UR, it'll tell you what's the host name. So what I'll try to do is I'll try to run my container or run that command that is run this command in a different namespace, in a different UTS namespace. So to do that, what we can do in Go is, so let's just book attribute. Okay, so I can add something called clone flags, and I can say that please run the command I'm giving here in a separate namespace. Okay, so the namespace I want is clone underscore new UTS. Okay, so now what's going to happen is when my command is run, it's going to run inside a new UTS namespace, and I can specify the namespace I want it to run in, using this sysproc attribute thingy of the command cmd variable. So let's just try that and see if it works out. So let's go here and let me run the program. Main.go run, and this time I'll run bin bash because I want to see if my hostname can be, if the hostname is different. So first of all, I'll split my terminal into two, just so that we can compare it with the original namespace. Okay, I hope this is visible. So I'll click enter on the top here on the container. Okay, so now this shell is running inside the container process. Okay, and now if I see the host name of this, I see that it's sri9, and that is same as the host name of my host. That's not changed. So what I can interestingly do is I can change the host name. So I'll change the host name to container. All right, and now I can check what the host name is. I can see the host name is container. Now if I check the host name on my host, hopefully it should still show sri9, right? So we observe something, right? So the process inside the container, I have changed the host name of that to container, but the host name in the host has not changed. It's still sri9, and that happens because this process is running inside a new UTS namespace. So to reiterate, initially when I ran hostname, it was sri9 itself, because even though it's running in a new UTS namespace, it inherits the hostname of the original namespace, like the one it was all of the host first, and then I can change it, and those changes are not propagated or are not seen from the host. All right. So I hope now you sort of get an idea of one of the namespaces, at least the UTS namespace, and yeah, so one of the things we would like to do right now is, when I ran bash, when I entered initially, the host name is sri9. So it would be quite nice if when I entered itself, the host name was container. So what would then happen is my terminal prompt would show container instead of sri9. So I'll sort of try to achieve that. So we can sort of do that with a command. So there's something on a set host name, and I can say let the host name be container, and I probably have to typecast it, so we'll just do that. Okay, so this command, what it'll do is it'll set the host name, but we'll have a problem. So the issue is, so maybe to give you a picture of what's happening. So what I'm doing is I'm running this program, right? Go run main.go run, and I'm running some command, say bin bash. So when the the code hits this line, it will spawn a new process. Let's say like this, and that process is bin bash. And since I mentioned the clone flags here, this will be inside a new UTS namespace, right? So the issue is I cannot write this command after this command is run, right? Because by the time after the command is run, the bin bash has already exited. So change the host name now is pointless. But I also can't run it before. Why? Because this part of the command, when this part of the code is run, I'm still in my host process, right? I'm still here. So when I run this, if I run this command, it's going to change the host name of my host. It's not going to change the host name of a container. So I can't run it before or after. So what we will sort of do is, to get around this problem, we'll create an extra process. So what we'll do is, because I cannot change this, I cannot change the namespace, the host name directly of bin bash. I'll sort of create another process and have that call this. So and this process will be in the new UTS namespace. So I'll write the code for it, and I hope it'll sort of make sense once I write the code for it and you guys see. So what I'll do is I'll copy this entire function and create a new child function, right? And what we'll do is, so we want to add a new parameter called child that runs a child function. So what we are going to do is, initially we are going to run this command, and that command will will run itself. So go run main.go run, it will run the program go run main.go child. So it'll run itself and it'll just pass the first argument as child, and then pass the same command back, same command to the child. And then what we say is the namespace of the child is a UTS namespace. And now what we can do is, this child is completely in our hand, in our control. We can change the host name of the child, and we'll be able to see that in the bash itself. Okay. So okay, let me just do that so that you sort of get an idea of what's happening. So when go run main.go run is run, it's going to hit this function. So here I do not want to run the program, the command program given. Rather, I want to run itself. So I can do that using proc self exe. So we'll look into this proc folder later on in detail. But what I'm doing is I'm trying to run the program itself, and I'm passing the first argument to be child, and along with it I'll pass the along with that I'll pass args after 2. So all the commands are passed. So we'll just do some Go stuff so that the compiler is happy. No. Yeah, the compiler seems to have some issues.
You need to remove that byte thing.
Oh yeah, it should be string. Sorry, yeah.
Correct.
Okay. Yeah. So what I'm doing is I'm basically running this command: go run main.go child, and the process bin bash. So I'm assuming the command given is bin bash. So in here I'm running the command. I'm running this command. So note that. So it runs this command. It runs it in a new clone new UTS namespace. I'm not going to set the host name here. Okay. So this process has run this process now. So the argument is child. So it's going to hit here and run the child process. So I'll come to the child process. So now when I come to the child process, here I'll run the same command, the bin bash command. So the command I'm running here is bin bash. Since this process is a child process, I don't need to set the UTS namespace again because it is already cloned by the parent process, and I have to set the host name just before here. So somewhere here should do. Okay, so I hope that sort of made sense. So feel free to ask doubts if this was sort of confusing. So I'll just repeat it again if someone didn't understand this. So initially we run go run main.go run bin bash. That will execute itself and change the run argument to child argument. And when it does that, it also ensures that this process is running in a new UTS namespace. Okay. Now this child process is going to run the bin bash, and since the child process in the new, so since this process is in the new UTS namespace, even the process that spawns the bin bash will also be in the same UTS namespace. Okay, so I say same to sort of convey that. And so right now in the child we have complete control before I start the bash program. So here I can set the host name as container and we proceed. Okay, so I'll just show you the output of this to show you that the hostname thing is working out. So previously, if you see here, when I ran go run main.go run bin bash, the hostname was sri9. So right now I've set in the program, I've set it as container. So when I run bin bash itself, it should run contain. It should go into container without running a separate command. So let's see if that works. Okay, so we see that it's telling it's running bin bash 2 times because in the code I have logged it twice, once in the main program in the run argument and once in the child process that spawns. And we see that the host name is container now. So if I see the host name, put the host name now here, we see it's container, right? So I'm able to virtualize the host name thingy. So the container has its own host name, that's container, and in the host it is sri9. So I hope up to this point it's sort of clear for everyone. Feel free to ask me any doubts. So I'll just check if there are any doubts. No, so nothing yet.
Also, if you guys are wondering why it's called clone, it's because the system call in Linux is called clone, and clone flags are basically the flags you need to send to the system call. So when you're starting a new command, it actually, so you would have heard of fork system call, right? So the clone system call is similar to that with just more, options available. So yeah, like if you want to look deeper into this, do go through the man pages of these system calls for that's fork and clone. Yeah.
So okay, so since there are no doubts, I'll move on and I'll create one more namespace. That will be the PID namespace or the PID namespace. Okay. So now what we'll try to achieve is we'll try to see that the process inside the container. So right now, if I go to go here, if I do PS or PS AUX, I'm able to see all the processes inside the host. I can see everything. So what I want to do is I want to restrict the view of the container. I don't want the container to be able to see all the process inside in the host. I want it to only see the process that it has spawned, that the container is has spawned, but I don't want it to see anything else. So to do that, I will be using the PID namespace, and I'll try. So I'll try to run the container in its own namespace, in its own PID namespace, and we'll see if it will work out or not. So since I've already written a lot of code, doing this would be very simple, So in clone flags, I just have to add one more flag. I'll say syscall dot clone new PID. Okay. So right now, the child process that is starting, it'll start with its own new UTS namespace and also a new PID namespace. Okay. And before I run it, we'll also add some debugging stuff. I mean, some output so that it makes sense. Yeah, so for each of the printing logs, I'll also put the process ID Also, by the way, PID is short for process ID. So in case I forgot to mention it, so process ID is something unique for every process. Okay, so all I've done is I've added just one new code, one new flag here, and just change the print statement, nothing else. So let's see if this works. So I'll exit on the old container instance, and we'll run the container now. So I'll press enter. And now we see something interesting. So initially here we see the first printing to show it's 29780, and the second one shows 1. So what happened is, so the first one was printed, if you remember, in here. So that was the process, that was the main process itself, and that was running in the host, right? The second one was printed inside the child, and that was printed inside a new namespace, inside a new Pid namespace. So what we see is, in the new Pid namespace, this process has process ID 1. Okay, so process ID 1 is, if you don't know, is a pretty special process. So if I just do ps aux in the host and look at all the process list, the first process, so root it's owned by the root user, it's Pid 1, and it's always will be the init process. So init process is the first process that runs in the Linux kernel. But what we see is that inside the container, this one PID is referencing to the first process that's running. So that's a child process. So as Aditya had mentioned now, as previously, so the same PID 1 inside the container is the child process, but in the host, it's actually the first, the init process that was running. So sort of now we know that the Pid namespace is working out, right? Because it is having the PIDs for the new for the container are now starting from 1. Okay, but okay, so what we should so we'll just try to confirm that this is working out by running ps. So I'll run ps aux, but we can still see all the processes, right? We can still see all the processes in the host in my container. So why does that happen? So the thing is, the container is running inside the Pid namespace, so that is correct. But this ps command, it reads is so how does the ps command work internally? So what it does is it looks into a file. So I'll go into I'll go into the root directory in my host, and maybe we can just, okay, so I'm in the root directory in my host. Okay, so what Pid does is, it basically, so there's a special directory in Linux called /proc, and Pid and /proc contains information about various processes that are running in a system. So you can see a lot of numbers here. So these are all the PIDs of processes currently in a system, and inside each of them, so it's like it's a folder, as you can see, and inside each of them you can find a lot of information about each of the processes. So the ps command is basically looking at into this file, right? So for example, so that we can just get comfortable with the proc command a bit. So if you remember, in here I had used this special proc self exe, right? So we'll just see what is there in that file. So ls proc self exe. So we'll see what's in this program. So you can see that /proc self exe is pointing to user bin ls. So that's the program I'm running. So what it means is, this file is pointing to the executable that I'm running, that's ls. So ls, and I can sort of see the PID, I believe, if I just do this much, yeah. So you can sort of see that this ls program is getting different PIDs each time I'm running, right? Okay. So now we're coming back to the container problem. So the container is now able to print all the processes because if you look at the root directory of the container, you can see that the container has access to the root directory of my host. What that means is it also has access to the /proc directory, hence when I run ps, since it has access to the slash proc directory, it's going to print everything that it can see in slash proc, and that's why this isolation, like the ps command, is not working, right? So how do we get it working now? So how do we sort of fix this problem? So any guesses to how we can fix this? So I hope everyone got the problem, right? Why even though we're in a new PID namespace, PS is not showing just the process in the container? So because it can access the slash proc directory in root. That's why it's showing all the processes in the host. So any guesses as to how you can solve this problem?
Like changing the root directory to some place where only the processes of this container are shown.
Correct. Yes, that's exactly what we should do. So yeah, nice. So let me do that. So let me go to this demo. We'll exit from the container. So if you remember, previously I had shown you how to chroot into Ubuntu FS, right? This file system that we already had. So if you can see in this file system, there is a proc folder. And this proc folder will be different from the proc folder in my host. So what we'll do is we'll change root into this Ubuntu FS, so that PS will now only be able to see the proc in this file system, and hence it can't see the process in the host. So let me do that. So we'll have to do it in the child, and it's a pretty simple command to do it. So we just have to say, I think os.change chroot, or syscall maybe. Yeah, it's chroot. I have to say it's Ubuntu FS. That's a file that I want the new root to be. And also it sort of is undefined if you don't specify which directory you should be in after chroot. So I'll just also mention where I want to be. I want to be at root folder. Okay. Okay. So once I run this command, let's go here. So right now, okay. So let me just run it. Go run bin bash. Okay. So now we see the same output as before. You can sort of ignore this warning. That's not a problem. So now if I do ls, I'm inside a different root. So I had sort of marked the root of the host with a file called root for host. And so now we can clearly see we are not in that directory. So I can do ls. I can try to go higher, but I can't. So now I'm trapped inside this Ubuntu FS file system. Okay. And the proc of this is empty, and which shows that that's not the same as the proc of this. Okay. So let me try to run ps now and see if it works. So it doesn't even work now. So now the issue here why that doesn't work is, so this slash proc is a special directory. So it's something we call a pseudo file system. So a pseudo file system is a way in which the kernel interacts with the user. The kernel will sort of dump information from the kernel side into these files. So into these files here. So these files keep changing dynamically, and the user space applications and process can sort of look into these files and get to some information out of it. And the issue is, as I already showed you, if I do ls proc here, that folder is empty. So by default, there is nothing inside it. So what I should do is I'll have to mount the proc pseudo file system into the slash proc folder. Only then it will start working. Okay. So when I run ps, it itself tells me, right? It only is telling me that please mount your proc and do something. So we'll just do that. So that just takes one command, and after that one command, we should hopefully work. So syscall.mount, we'll have to mount it, and yeah. So the attributes will sort of not make sense if you just look at it like that. So this proc because okay, I don't remember the order of these things, but one of them is saying it's the slash proc directory, and one of them says, I believe it should be the proc pseudo file system. So there's a proc file system that I have to mount into the slash proc directory, right? So I think rather than this command, this sort of conveys it. So mount -t proc slash proc. Okay, I'm not sure why there are two procs here, but what it's saying is that you have to mount the proc sudo file system into the slash proc directory. Okay. I will find out why there are two procs and let
Because
you know.
the proc is also a type and also the name of the file system. So there can be different file systems like types like ext4, NFS, and all those. So proc is a
Okay.
separate type. So -t proc specifies the type of the file system, and the second proc is the name of the file system, which is again proc.
Yeah. So that's why when you write it in the the Go language, it sort of really. I mean, it's very easy to write, but yeah, it can be confusing. And also, let's remember to unmount at the end of the process, so that we don't have something hanging after the process quits. So we want to unmount proc and the second parameter flags as 0. Okay, so now we are mounting the proc file system into the slash proc directory, and hopefully now it should finally work. So we'll go back to here. We'll exit from the previous container instance and run it again. Okay, so now let's run ps. And now we see I can see my PIDs from 1 to 6, and even if I run ps aux, that lists like all the processes, I can only see 3 processes. I can't see more. And in the host, clearly there are a lot of processes, right? And my container is not able to see any of them. So now we have achieved the isolation of the process also in the container. I mean, we had already achieved it, but now we are sort of got the PS also working out. And so, for example, if I run some command in my container now, let's say sleep 100, I will not be able to see it. Sorry, if I run sleep 100 in my host, I won't be able to see it in my container. So I can do ps aux. I can't see it. But if I run a sleep command in my container, I can still see it in my host. So see, I can see this. And you can do something interesting. So let's look at the proc directory of this command. So I can do ls -l /proc 33291. This is in the host, and I can see what the root directory of this process is. And you will see that the root directory is pointed to home something 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 and Ubuntu FS. So that shows that this process is ch rooted into the Ubuntu FS file system, the files folder. Okay, so I think that should be. So we have seen how to isolate two namespaces. So we have isolated the UTS namespace and the Pid namespace. So I hope that sort of gives you a good understanding of what's happening. In a container, you would be having different namespaces. So I've only shown UTS and the Pid namespace, but in the container you would have namespaces for pretty much everything. So all of them would be so process running inside the container would have all be in different namespaces than the host, and different containers would be in their own namespaces. And that's why processes in each container, so two processes in different containers will not be able to see each other because they both are in different namespaces, sort of, right? So for example, two processes, one process running in container 1, second process running in container 2. So since the PID namespaces of both the processes are different, they will not be able to see each other, right? So yeah, so I hope that makes sense. If you guys have any doubts, please feel free to ask. So I've been writing a lot of code here and doing a lot of stuff with terminal. So hope that makes sense. Yeah.
Can you explain once again how did you connect the PID namespace with the mount? Like, how did the mount know from which PID to take processes in the folder?
So see, so the ps command by default will look at the /proc folder, right? So it look at the /proc folder. So the problem was once I ch rooted, the /proc folder was empty. So if I do ls /proc now, it's not empty. It has a lot of contents, and that's because I've mounted the sudo file system this is the proc sudo file system into /proc. So if I look at all the mounts, I'll see that the proc is mounted. Yeah, so as Aditya mentioned, proc sudo file system is mounted on /proc with type proc. Only because of this mount, PS is working, right? So the pid namespace was working even before I did the mount, but what was the issue was the PS command was not working because PS was not able to get the information from the kernel. So to do that, I had to mount the proc sudo file system into /proc. So does that answer the question?
Yes. So now there are two duplicates of the same process folder, one in the host proc and one in the ch rooted proc.
Correct, but they are not same because I can sort of ls the /proc in both of them. So if you look at the /proc of the container, there are only three processes: 1, 16, and 6. So these are only the processes in the container. And now if I do ls proc in my host, there are a lot of processes. So the proc folders in my container and in my host are not same. So the proc in the container will only have processes inside the container. So is that okay?
Yes, that's fine. Thanks.
Yeah. Yeah, so I think so I conclude the namespace part here. So we can also create other namespaces like mount, network, user, and all that. So I won't cover that in Go for now, but so I hope this sort of gives an idea of how namespaces work.
I think you can also show a demo by running strace on Docker, like how these namespaces are called.
Okay, wait, let me. So how do I run it? Okay, I don't think I have strace installed. If it installs fast, I can show it. Okay, I install fast. Yeah, so I have strace installed now. So strace, so is it
The same command that you ran earlier, you just prepend with strace, yeah.
okay, so Docker Ubuntu, and I'll just run sleep maybe. That's fine, right?
Yeah.
Is it fine? Okay, so will I have to grep something? Or maybe I'll put it to ls.
Yeah, anything is fine. I just show system calls, so shouldn't be an issue. Okay.
So what should I find for? Yeah, I was afraid it'll just. Okay, it's sort of stuck. Okay, I'll just remove this.
Can you find?
Yeah.
Hello.
Yeah. Hello. Yeah, this is not working out. We'll just put it into a file.
I think forget sleep, just do ls. The sleep is like 10-second wait. Just do ls and then get the dump.
Okay. I'll just be in the correct folder. So yeah. -rm Ubuntu. I'll do ls. I'll just put it in a file called trace.dump. Yeah, just trace.dump. It should work.
I don't think that'll work. Anyway,
Oh, it's std error. It's it.
No, like that is like part of the
Ampersand.
command.
Yeah, you can do ampersand arrow.
Or is it 2 or ampersand?
Ampersand should work. Everything will go to trace dump.
Oh, okay, fine.
Yeah.
I think it should be Ubuntu.
Thanks. Yeah. Okay. So what we want to find here is clone command. Yeah. So if you see in the strace, so an strace of a process basically gives you all the system calls called, right? So if I see the strace, so if I zoom in a bit, yeah. So here you can see in a system calls called there's a system called clone, and what is it cloning? So this is not cloning a new one yet. Maybe they call unshare, not this. So let me see.
There's search new NS somewhere. That should be there. No. Okay. Wait, what is the flag?
Yeah, so we are expecting to find some system call related to namespaces. So yeah, we have not tried it, so we may not know how to find it. I believe unshare will be called somewhere. Yeah, I guess we're not doing it right. Yeah, so I'll just spend maybe 15 more seconds on this. Maybe just. Yeah, so I'm not entirely sure what the issue is. So yeah, so what we're expecting to see was some reference to namespace function call. So we are not seeing that. So anyways, so if I'm able to do this before the session ends, so I'll show it to you guys. So since we didn't prepare for this, I'm not entirely sure what's wrong. So what we should have seen was we should have seen some clone command with cloning one of the namespaces. So it could have been a mount namespace or a pid namespace or anything like that. Okay, moving on. I think we have one more topic to cover. So yeah. So if any of you have doubts, you guys can ask it now about namespaces.
Okay, I think I searched in internet. The issue is that since Docker contacts the Docker daemon behind, we are just stressing the Docker.
Oh,
The Docker
correct.
client. It's a Docker daemon that's
Yeah.
it, right? Yeah.
Oh, right. Makes sense. Yeah, I'm not sure how to run stress on the Docker daemon.
Get the PID of the Docker daemon and just trace that.
Okay, I'll do that in the background maybe. Yeah.
Later.
Yeah, later on.
Okay. Yeah, I guess we can move on. Any questions, guys?
Yeah, I'll just check. I don't think anything new was asked. Yeah, no. So I'll move to the next slide. Yeah.
Okay. Yeah. So the next thing is C groups. So yeah, like there's not much to tell about this because this is the definition that C groups are used to, so we saw how we can, present a different isolated world to a set of processes, which basically makes a container. We can give them a new file system and using different namespaces, completely, separate, virtualized, environment. But how do we limit? But still, it's using the resources on our host, right? So how do we limit the resources they use, say the RAM or or CPU? Yeah. So that is where C groups come in. So C groups are, used to apply certain limits and, to the resource usage of usages of a certain group of processes, right? And yeah, this diagram sort of explains in a very simple way how C groups work. It's kind of like a negotiation that processes request for more resources, and then the kernel tells them that can they have it or not. And yeah, we can continue to the demo then after this.
Yeah, just give me a second. Okay, so let me. Okay, so I'll close this. Okay, so about C groups, let's first look into. So I'll go to the root folder. So you can find so C group is another kind of pseudo file system like /proc, and you can find it in sysfs C group. So inside this you find a couple of folders. So this it's like a pseudo file system like ps like /proc. So we can go into, let's say, memory. So what we can see is in memory, let's actually cat into some file. So memory dot limit in bytes. Okay, so this C group is so we are in sort of the default C group that every process sort of gets, and so we see that this is a huge number. So what that says is that by default, any process that you start, it's going to get all the it can potentially take all the memory available in the system. So that's why you see such a huge number. And so in here you can see a file called Docker. So that's interesting. So this seems to be created by Docker. Let's just go into that file. And again, in Docker, you see a couple of files. And if I again cat memory limit in bytes, it again shows a huge number. So what I'll do now is I'll start a Docker process and we'll see if there is any change happening in this file in here. So let's start Docker run. So same command, Docker run -rm -at ubuntu bin bash. I'll run this command. So I ran this command. So let me ls in this folder and see if anything changes. So let's see if we see anything new. So we see this huge folder with a lot of letters. And if you look at the prefix 06AA, that corresponds to the prefix we see here 06AA. So that tells that this file was created with respect to this Docker run. So let's see, for example, the memory limits which I was seeing so far. So let me cat, let me see inside this folder, and let me see the memory limit in bytes. We see that the limit in bytes is again a huge value, like 9223. I mean, a lot of characters there. So now what we'll do is I'll run the same Docker run, but I'll pass in an extra flag. So in Docker, you can sort of constrain the amount of resources that a container can take. So I'll constrain the memory. So let's say memory is 10 megabytes. And I'll run this program. So let me ls again, and I'll see that this new file is created, d1419, that corresponds to this container. And now if I cat d149 and do memory.limit in bytes and press on enter, you see the value is much lower, right? So this basically corresponds to 10 megabytes. So that's sort of how C groups work. So what you can also see is, or rather I'll talk about it later. So So I hope this sort of gives the understanding of what C groups are doing. So it's like a pseudo file system where you can mention some constraints, and the point is that under each C group, so in this file D149, I'll cat a special files called cgroups.pids. Okay, so that's not there. Cgroup.proc, sorry. Yeah. So what it is doing is, so in in this file there are a set of constraints on memory. So for example, I saw that in memory.limit in bytes there is a constraint, but how do I know which of the processes should respect this constraint, right? How do I know that? So so this file cgroup.procs will tell me which processes are going to respect the constraints given in the C group. So 39420 is corresponding to the bin bash process that's running in the container in the host. So for example, if I run another process here like sleep 100, you will see that there's one more process that will come up here because there'll be a child process of bin bash. So let me do cat here, and you see 39990. And if I ps into that process 39990, that is basically the sleep process that's running in the container. So basically any process that's running in the container is now constrained by the C group rules as present inside this folder. So I hope that makes sense to everyone. And I'll sort of also give a demo of it by extending our previous Go code. But I hope until here it sort of makes sense. So I'll exit from the container. So in C group, we see a lot of files. So there's something about memory, something about CPU set, something about bits, and so these are all different resources that you can constrain for a process. What we'll try to do now is, for this container that we're writing in code, we'll try to constrain it, and we'll constrain the number of processes that we can launch inside this container. And we'll do that by constraining the number of PIDs. So that will directly constrain number of bits, a number of processes. So we'll go into this bits folder. We'll ls into it. And yeah, so as we can see in the bits folder, it has the same sort of structure. So there's a cgroup.procs that tells which of the processes are going to respect the given are going to respect the given resource representation, right? So we'll be specifically looking at something. So if I go to docker pids.max, so pids.max is a property that says what's the maximum number of pids I can launch in my container, and by default it is max, which is the maximum limit that maximum limit of your host, right? But you can constrain it to a given specific value. Okay, and I'll sort of write code to do that now. So what we will do is, so in this directory pits, I'll create a new folder, and I will I'll set the pits max inside that folder to be 20. So it's restricting it to 20 processes, and I'll add in the C groups the container process, so that the container process is constrained by that C group rule. So yeah, so it's just, so let's call a function called cg, and we'll call this function here. Okay. Okay. So initially I'll just so this will have the up to, no, it should be sys fs C group. It should be C group, right? Yeah. So C groups will contain the path up to C group, and yeah, or rather we don't need to do that. We can just do PIDs. So we'll save the path up to PIDs, And what we'll do first is we will create a C group rule sort of, right? So for creating one, I'll create a directory inside the spits folder. So I can do that with os.make directory. I'll call this rule as let's say, so okay, first of all it should be in pits plus container, and the second parameter should be the file mode. So I guess it will be 0755, right? So I'll create a directory inside this pits folder. So as I already mentioned that C groups is a pseudo file system. So when I create a directory, it'll create a bunch of files. So as soon as I create a directory, it's going to create the files. So I'll go into PIDs. As soon as I create a directory, it will automatically create these files for me. I don't need to create it explicitly, right? So it's going to create pid.max and stuff like that. So what I'll do is for the pid.max value is present here, I'm going to replace that. By default, it's going to be 20, as I already mentioned, going to be max. I'll change that to 20. So to do that, we will set max PID. So we are going to write to a file, and the folder location of that will be PIDs plus, container and PIDs.max. So I hope that I got that right. Yes, PIDs.max. And the second one is the data I'm writing. So the data I'm writing will be 20, and I think we have to just typecast that. And the third parameter should be the file modes. Just give it this. Okay, so I will now set the max PID to be 20. And just doing this won't work because I have just now created a C group with some container name, but I have not said that my container process should belong to the C group. So to do that, I'll have to write my process into this file. So this file that's present here, cgroup.procs, I'll have to write my process into this file. So to do that, I'm going to do os.write file. So the directory of this process is going to be, let's see, container slash, what's it, cgroup.procs. So I hope I got that right. Yeah. And the content of this will be the process ID, right? And again, the file permission can be set like this. Yeah, so I'll have to, so this is what we want. We want to write the current process ID. So I'm calling CG from the child process. So I want to write the process ID of the child into this file so that the C group will apply to the child process. And yeah, so this is an int, so it's not happy, it's an int. Okay, so we will fix that. First, we have to convert it into a string. I think I to a. Yeah, so this is just Go stuff, so not really relevant. But yeah, we need to do it to get it working. Okay, so here we are add current process to C group. So we have added container. So we created the container rule, we have added PIDs max, and we have added the current process. And there is just one more thing we need to do, not really relevant to, just so that things sort of work out. I believe it's this. Notify on release. Yeah, this is just to, I believe it'll just deactivate the C group as after all the processes. it'll notify the C group after this process leaves the leaves the C group, something like that. So Yeah, I'm not sure if it's required, but to make it work, I just wrote it because I was not sure if it'll work without it. So, anyways, the two important things we really care about are this: we set the PIDs max to 20, and we have added the current process to the C group. Okay, and we have called this function CG in our child process. So I'll just cross verify once that everything is working fine. So PIDs plus /container / C group procs, not release. Okay, so it all seems fine. So let's hope it all works out. So
One doubt actually I have. So won't os.get PID return 1 because it is already in the new process namespace, PID namespace?
That is true. os.get PID does return.
It was returning 1, right?
It was returning 1, correct. It was returning os.get PID was returning 1 here. So the child process is going to. Yeah, that's actually a good question. I'm not entirely sure, but I know that this works because I tried it out, before the session. I
Okay.
guess it sort of is smart enough to figure out the actual PID in the host or something like that.
Okay.
That's the only guess because ultimately this process is still visible to the host, right?
True. Yeah.
So it can maybe get the effective PID or something. I'm not that sure.
Yeah. It makes sense. I guess it figures out what names, like if the process is running in a namespace and then tries to find out the actual PID.
Yeah, I think that sort of works out. Yeah. Okay, so let's first go into maybe home demo, or we don't. Yeah, we need to go there, right? Because my file is there. So I'll go into the place where my main.go program is present, and the second terminal I'll just be in root just in case I need to do something in the root as being a root. Okay, so now I'll run my program, and hopefully it'll work out. Okay, so run the program, and let's check the C group. So let's go to the C group file first. So we created some rule under PIDs. So let's go inside PIDs. Let's ls, and do we see a container? Yeah, sadly we don't see a container. That means it didn't work out. So I hope I didn't make a spelling
Is
mistake.
this file in the root folder, main.go?
Oh, right. Thanks.
Yeah.
Yeah, so I had forgotten to mention the root here, and that's why I think it failed. So let's run it again and see if it works out. And now if I do ls, yeah. So we see a container, right? So this Go program now created a container C group. Let me go inside the C group. Let me ls. So there are some files here. Let me cat pids.max. It's 20. Let me cat the C group procs. That will show me the current process that's running inside my C group. And it does show two processes, 43757, 43761. So to prove that these are the processes of the container, what we'll do is we'll run sleep command, sleep 100. I'll get the PID of the sleep command in the context of the host. So that is 44057. And since this sleep command is a child process of the bin bash command, and since the bin bash command is already part of the C group, this sleep command also should be part of the C group, should be added automatically. So let me cat C group.procs, and we see this process 44057 in this, right? So that means our C group is working correctly. It's accounting for all the processes that are running inside it. Okay, so now so now what we have achieved is we are able to constrain the number of processes running inside my container. So we can sort of test that out. So do folks know about something called the fork bomb? So what that does is it's a short terminal program. You can write it, and what it'll do is it'll create a lot of processes very fast. So it will create exponential number of processes in a given amount of time. And what can happen is if you run such fork bombs on your normal computer, your computer will probably just crash, and you get stuck, and you'll have to probably force reboot. So what I'll do is I'll try to run such a fork bomb in my container. And if the C group thing is actually working correctly, the fork bomb should not work, and it will sort of fail off and tell the resource is not available or something like that. And if the C group thing is not working correctly, then yeah, probably I'll I'll leave the call, and I'll have to rejoin because my computer will get stuck. Okay, so let's see. So a simple fork bomb there is you define a function called colon. So this is batch script, and you call colon again, and you pipe the result to the same function colon and run it in the background. Give a space. So this is a function, and at the end you call colon. Okay. So this function colon is called several times. It's called here, and so one call of colon is calling 2, and those two will call 4, those two will call 8, 16, 32. So you see how it explodes fast. So so if the C group thing works, this fork bomb should fail because this can't create more than 20 processes. Okay, so I'll just verify once that this C group is working correctly. Okay, so 2 of them are present. PIDs.current has number of processes running currently, so it says 5. Okay, so hopefully this won't work. So let me run this program. So you see this, right? So the fork bomb is trying to create as many processes as possible, but you see it complains that bash fork created a resource are temporarily unavailable. What that means is it's being constrained by the C group. And how do you sort of prove that? So this file PIDs.current will tell me all the PIDs that are currently in the C group. So I can cat that, and it's saying 20. And since I said the PIDs.max to be 20, my process can't create more than 20 processes. Sorry, my container can't create more than 20 processes, and hence it fails. Hence it says resource temporary unavailable because C group is not allowing it to get so many processes. Okay, so yeah, so that's nice, and you can sort of see this process. So you can do PS, I think FAX. I can sort of show you. See, so this is the Go program that's running, and this is the child process, and you can see that this bin bash has created a lot of defunct processes. So these processes are defunct because they're sort of like zombie processes. They are run as child forks of the parent process, and the parent process is not collecting them, or the parent process is still waiting, and that's why they're still defunct. And because of them, you can't the C group. Because of them, PIDs are allocated for all these defunct processes, and hence you can't create more processes because I have set the PIDs to be max 20. Okay, so I'll just stop this process. So hopefully now you get an idea of how C groups work. You can sort of constrain the amount of resources that can be used by the container by C group. So namespaces. So to summarize, sort of with namespaces, you can constrain. You can make sure you can constrain what the container sees, and with C groups you can constrain how much resources that the container can use. And if you mix that with chroot, you pretty much can implement a very basic version of a container. So right now I'll just exit of the container. This program here is a very basic version of a container, right? So it has its own UTS namespace and PIDs namespace. So the process running into the container can't see the host process, and also the number of processes that I can launch in the container is constrained. It can't be more than 20. So it sort of has some basic features of a container. So if anyone has any doubts, you guys can ask me about C groups or namespaces or about any part of the demo.
Do we have any more slides? Okay. Yeah.
No, I think this is the last one.
Yeah, I think we can share the PPT link. Yeah.
Okay.
So again, this PPT will be available here. You can access it. The code that was written will be available at the GitHub repository. And yeah, we are open to questions now. Also, don't forget to attend tomorrow's session, which is gonna be about Kubernetes and just not just Kubernetes but container orchestration in general. Yeah.
So you guys were comfortable with C groups and all that, so like, yeah,
I
it
was
might.
actually expecting some doubts. So yeah, any confusion or anything?
Yeah. So the question thing is not closed, right? Hopefully it's still.
It is open. It is open.
Okay, fine. Wait, it shows closed to me.
And I guess you have to present it, and you can continue them. Like I've kept the link open, so you should be able to.
Okay, something weird. Maybe I'm opening the wrong link.
Ayo. Wait, I'll reload. Try now. I don't know.
Yeah, it's weird. Yeah, you guys can ask, unmute and ask as well, so no issues with it. Should I try out that S-trace thing? Because that Shashank was suggesting.
Also, guys, this tutorial today was heavily based on video from in a conference, from a talk in a conference, which is called Board 2. I'll share the YouTube video. You can always watch this and get a good understanding. So this is from the year 2018.
Yeah, so let me just try that idea that this Shashank mentioned. Okay, so we want to. Okay, let's see. I want to get to the Docker daemon, right? How do I get the process out of the Docker daemon? Should I do systemctl?
I guess you can do Docker D, right?
What, not found? System ls, is it? System. How do I see all the daemons in my system?
I'm not sure. Just systemctl list units, right?
List units.
Hyphen, I think.
Docker does it. Okay, it's just Docker.
518. 518.
518. Okay. So S-trace. So let me go into the demo folder first. So I had to probably be sudo, right? Let's trace that S-trace.
Just the
so I
PID.
just said
Just the PID.
just the PID. Okay. 518 trace term. And
you can ls, like you can just less it and search in that. I guess you can see the live output.
So Docker rm Ubuntu ls run. So in here I'll just have it running.
I think you have to hyphen p, I guess.
Hyphen p. Cool. Okay, I should. Okay. So the trace should come out. Huh? What?
Just remove the trace dump thing. Just do one pipe it to less.
Is it because of sudo?
I'm not sure. Yeah, probably. Does it create any child processes? Not sure.
I think other things are handled by those run C and containerd. There are still
Ah,
many things
yeah,
available.
yeah. I
So
guess
run C is one I should see here.
internally it uses run C.
I don't think it's a executable. Run C. It's a library or
No, I mean it will still be in the context of the process, right?
okay. It's
But can I stress into the child also? Is that possible?
If you have the PID of the child, you can.
yeah, you can do -p PID.
No, but can I have stress following it? Other like it also stress a dump of all the PIDs, like not just the parent, but also parent and the child.
I'm not sure.
Recursive one. Don't
I
know.
think it should be possible.
It should be, but I don't know how you do it.
-f flag. Huh? Okay, let's see.
No, wait. It should be the Docker daemon itself, right?
Correct. Wait, I'll try. Okay, maybe. Yeah. -f. Docker run ls. So s is -p -f. Okay. Okay, so we have some terms. Okay, we see something. There is setness. Definitely will have a new PID. So new PID also. New net is there. So it's being setness.
What are clone flags have been passed? Just do clone underscore.
You can just find all the new namespaces. Only new net.
Interesting. We're missing something.
Yeah, I mean it should definitely do new PID, right?
Yeah.
I think some won't be visible. Stress will put a limit on the length of the string. Can you see dots in the arguments somewhere?
Dots, huh? Okay,
Yeah,
there are dots somewhere.
not
Okay,
that.
you mean in the
In the
no, it's
inside the brackets.
in the which one?
So for a lengthy argument, I think it will just add dots instead of writing the
But
argument.
okay, maybe okay. I'll try for clone command match case. It should be present of clone. Okay, maybe it's present here. Maybe I'm not sure. Process.
I think you can run stress minus s to control the length of the string. I don't know. I think it's minus s. Not sure.
Okay, not complaining. What if I try on this itself? I don't know if it'll work, but yeah, just trying. Docker run minus rm trace. Okay. Okay, when ls output. Okay, I don't want ls output. 2, right? ACDR. Yeah, it should work. Hopefully. Yeah, that is useless.
Maybe try E option. You can specify a specific system call in that. Just look for clone system call.
Can I specify multiple?
Instead of doing that and trace dump, just do -o trace dump. Probably there will dump everything.
Hyphen.
-o the output.
Okay. Can I have multiple?
I guess you
Minus
can
E.
give multiple -e. Yeah.
And we also set NS.
Achha, you have to give -e trace is equal to. Then you can give multiple. Small. And caps.
This.
Yeah, comma separated. Not. Yeah. Remove those extra -e and separate the.
It should be a string.
No space between commas. Yeah.
15 threads. 15 threads. Okay. Okay, there are some high processes that is interesting. That is not that, but there's nothing in this. Okay, it's only.
Do you have ps tree command? I just searched in internet. It will show the tree of the processes created.
PS tree, yeah. Yeah, I have.
Yeah, I think you can.
In strace, just give -v. It won't truncate.
It won't?
Truncate. Just give -v.
Okay. So minus is not required, no? -v. It's still all in unit.
And give that -s also. -s you give to 1024. Let's see.
Okay, those unshare system calls and all will be called by containerd. So I don't think we can get it here.
Containerd, fine. We'll see what containerd is. It's okay. Maybe it becomes active when only there is. Okay,
No,
I have to
think that's how it works.
Okay,
we can look into it later, I guess.
Yeah, fine. Yeah, so yeah, I'd seen who's that guy live overflow video where he does this. I don't know what he's tracing there. He sort of shows one of the unshare commands, I think. Unshare or any one of the unshare clone or setness, I'm not sure which. Yeah, stop presenting. Oh, there is some message. Oh, that's YouTube. Okay.
Chalo. Okay then. Good session.
Yeah. Yeah, I just stop the recording.